already gave me that. We have recitation week 12 paper. That's this week at recitations. We have homework 6 due Wednesday. I'll be there at office hours. And we have Wednesday, Thursday recitations. And Sunday, we have the exam review. This is a regular class material. So this Sunday exam review, it's not an honor thing. This is not honors discussing extra hard problems. The Sunday exam review is specifically targeted at your final exam. Okay? So this is non-honors. And we have trace evaluations. How many people have done the trace evaluations? Can we please do them? Okay? Be honest, say the good things and the bad things. Now, today is our last class, right? Are we happy about that? We're happy. We're still going to see each other, right? Wednesday and Thursday. But that's the last time we see all of us together. So before I start, which we have to finish graphs, we have to talk more about graphs. Actually, graphs never finish. It's one of those things. It's all completely open-ended, so we can't finish. But we'll do a little bit more. I have an important philosophical question for you guys before I go into graphs. Which is, you guys came here in September, right? After high school, right?
Yeah.
Right. They took a lot of adaptation, and let's see how it goes. I was not sure how the college is gonna go. You perhaps still not sure. But 3 months and a half passed, right? You have a better idea now, presumably. If not about the college, hopefully better idea about yourselves. So my question is, what really matters?
Nothing.
During college. I would say during college years. Have we answered that question yet? Like, what's your plan for the next 3 years and a half? At some point, you're gonna have to make a plan. So let me put more context on this question. I have an answer. The answer, you're all gonna agree with me, it's universal. Except the question is ill-defined. The problem with college years, there's two things to know about college years. One thing is that those are the best years of your life, by far.
They say that every 4 years.
No, let me tell you why. Before the college years, you have no freedom, no independence, no decision-making process. You depend on others heavily. After college years, you have too much stress and worries. There's mortgages to pay, kids to grow, you name it, right? So college years are the best years where you can make a decision that will change your life. Those are the 4 years that will have the biggest impact in what you're doing next. So I'm saying the college years are the most important 4 because you have your freedom now and your independence, and you don't have worries yet. Those will come soon enough, no problem. Worries will come. But before they come, you have 3.5 years to decide what to do. So here comes my answer to the question. In the light of what I just said, most important years, no worry, here's the answer. Don't waste your time. Time is a very precious resource. You have to make the best you can out of these 3.5 years. It sounds very, very easy. Don't waste your time, right? It sounds like a good thing to do, right? The problem is, this question is ill-defined. Wasting time means different things for different people. You gotta ask this question: what really matters during those years for me? Because different people will have a different perspective of what really matters. And the really difficult stuff with this question is that everyone around you will have an opinion with authority about what you should do. Your parents, grandparents, brothers, sisters, friends, teachers, everyone will tell you this is the most important thing. Like in 5 minutes from now, I'm going to say Euler's theorem for graph, the most important thing in the world, right? And next term, somebody's going to say functional programming, scheme or rocket, the best important thing in the world. That's the first thing you should learn, most, right? Your parents will say that's the most important. Your girlfriend, boyfriend, most important, right? It's a lot of noise. So you have to figure out pretty quick, how about we ignore all that noise and we figure out for ourselves what's the most important thing to do. Okay, I could easily say math is the most important thing, but the truth is, many successful computer scientists were not that good at math. Okay? So that's something for you to think over the Christmas break, so to speak. Because now we have to talk about graphs. So where are we? Here's the graph we saw last time. I'm going to use the same one. We talk about the adjacency matrices. How do we represent the edges, right? Edge is AC. It's an edge, right? For example. And I could represent that as the pair AC. I could write it that way, and it's an element of the matrix is the cell 1 of matrix, adjacent matrix, right? Which corresponds to the cell. If you look at the matrix, here's A, here's C, that's a 1. That corresponds to this element, AC here. So what I want to talk about now is the idea of a path, which is a sequence of edges. Let's say adjacent edges. So I'm going to write A to C. That's direct path because it's an edge. But I can write A, it is a little curvy thing, A to say F, that's a path. And it's made of the following edges. I can go from A to F by saying I go from A to C, from C to B, and from B to F. So my path from A to F is A, C, B, F. So a direct path means it's an edge. A path means it's a bunch of edges all connected together. I could have two paths. Another path, AF, is, in this case, I can go ADF, or I could go ADEF. All those are, let's say comma here, they're not equal. All these three are paths from A to F. If there's multiple paths, between two vertices. That implies there is a cycle. So in here, we have found the cycle. I could think about, I can go AC we said. So I'll copy this one here, AC, BF. But at the same time, I could go AD, EF. So I could visualize here, I have this cycle. Huh? ACBF, EDA, that's a cycle. So I could write it as, sometimes people write it like AB, ACBF, and then I get ED. That's my cycle right here. So this is an undirected graph. Which means paths and cycles have no direction. Again, this is undirected. That means the edge AC is the same as the edge CA. Right? There's no direction. So every cycle and path will be also undirected. A path, it's the same as saying reachable. That's the same thing. Reachable from A to C. That means if I can reach from A to C, I have a path from A to C. And the last thing that we, I think, saw last time was that I could have two components here. I could say this is component 1. I can have another component of this graph, component 2. Let's say I have G, H, and F. So the graph has two components, but there's no edge between them. That's why we call them two components. So there is a disconnect. Component 1 and 2 are disconnected. If somebody says I have a connected graph, it means it has only one component. Everybody's connected together. If I have a 2-component graph or 3-component graph, I can have more nodes that are disconnected to both those things. Then I have more components of this graph. Each component in itself, it's a graph. I could just look at this and say, what graph do I have here? Well, that's a GHF with 2 edges, right? That's a graph in itself. So each component, it's a subgraph. So each component, a subgraph. So of course, there is the whole theory of path, cycles, reachability, component subgraphs applies equally to directed graphs. Everything has to be modified accordingly for a directed graph. In a directed graph, of course, a path has to follow the directions of the edges, right? So if I have, I show you guys last time this other graph. Actually, I still use this board here. Had A, B, C, D. Here's what I have here. Notice that this is directed. So in a directed graph, the edge AC is not the same as the HCA. That's why I have 2 edges, because I want both of them in there. What would be a path here? AB a path? That's a path. How about ACD? Is that a good path, ACD? So I can reach, that means reachability from A to D, right? I have a path from A to D, so I can reach from A to D. How about from D to A? Can I reach from D to A in that graph? Can I? Can I reach from D to A? No. There is no path. From D to A. Now, see the difference between a directed graph and an undirected graph. In an undirected graph, if I have a path one way, or reachability one way, I automatically have the reachability the other way, because the edges have no direction. So if I can go on, from my house to your house, I can walk backwards too, right? Same path, same streets. But in a directed graph, like here's the water flowing through the pipes. If the water flow one way, there's no promise that it can flow the other way, right? It may happen, like do I have a path here? I don't think let's add an edge here. What about now, if I add this edge? Now I add, I'm going to say here, add edge BC, which is the same as saying B arrow C. If I say BC or B arrow C, that means the same stage, which is the same as saying BC. Those depends what notation you want to use. Those are the same edge from B to C. How about now? So let's, if I say reachability of D to A, right? That's what I was asking earlier. Is that possible to reach from D to A?
Yes.
How do I do that? D, I have to go to where? B. Right? Now, A became reachable from D. What's a cycle in here? Is BCD a cycle? BCD is a cycle? Right, yes. Because I can go from B to C to D and back to B. In a cycle, I have to reach where I started, right? So in a cycle, like in here, I have to reach from where I started. Here's another cycle here. How about ABC? Is that a cycle? Can I go from A to B to C and back to A?
Yes.
So we've seen those things: cycles, paths, and the one thing that we also saw last time was the idea of a degree. So what did we say is that here's a node. It has some edges. I'm not going to point all the edges. Let's call this node A. And here's another node, B. And there's an edge between them. And this guy has some other connections, of course. I'm not drawing all the graph. Just two nodes A, B, and they have edges. This edge AB contributes +1 to degree of A and +1 degree of B. Because if you count the degree of A, you count all the edges incident on A. So let's say that degree of A, count of edges incident on A. Or we can call them connections. Especially if this is a social network graph, how many connections we have. Now, in here, connections are reciprocal. If A is connected to B, B is connected to A, because it's undirected. If I do this on a directed graph, I have to specify what I mean by degree. There's an in degree. In here I have in degree of a node, like say A, and out degree of node A. So in degree of A is how much in here? How many edges come to A? One. Out degree of A? Two. How about in here? Degree of A is how big in here? How many edges are adjacent to A in this graph? How about in B? One, two, three, four, 5, 6, 7, 8. Those are the degrees. What you realize is every edge contributes 1 to both nodes that it's connected. It adds to the degree of this guy and to the degree of this guy, right? Because every edge is incident on 2 nodes. Now, in a directed graph, an edge contributes, edge say AB, contributes what? Plus 1 to who? For A, this edge from A to B contributes to which degree?
Out degree.
Out degree. And it contributes plus 1 to in degree of B. Still contributes 1 and 1, but from the source it contributes plus 1 to the source out degree and plus 1 to the destination in degree. So that should be enough to solve most problems you have in the homework and probably in the exam too. But let's do a little bit more of this. So here's a problem that now is very famous, and we know very, very simple solutions of it. Euler posted this problem in 250, 270 years ago. Euler Path. It means use every vertex. Exactly once. Use every vertex, edge. And if I replace path with cycle, do the same, and arrive where we start. Has to be a cycle. So if I put the additional condition, I want to come back exactly where I started. I'm not just saying use every edge exactly once. I'm saying I want to finish where I started. So here's a graph. I'm gonna see if I can draw this. I'm gonna call this 1, 2, 3, 4, 5, and 6. And I'm gonna have an edge here, an edge here, an edge here. This edge, this edge, this edge, Sir? Nope. I'm missing this edge. Right? This is a graph, has some edges. Question is, can I have an Eulerian or Euler path? Actually, I'm looking for a cycle direct. I'm not just looking for using all the edges, but I want to end up where I started. Now, I can choose where to start. But, of course, if I manage to run such a path, it's presumably going to go through all vertices, so I could have started in a different vertex. Is there a way to go through all these edges? Use all of them exactly once. So I have to use all edges, and I have to use them exactly once. I can't go twice or 3 times on the same edge. And I want to end up where I started.
If you start at 3,
Where?
you start at 3.
3?
Yeah.
Okay, so let's say 3. From 3 go where?
2.
I go to 2. I'm gonna mark here the edges that he's been using so that we make sure we're not using them again. From 3 to 2. So I use this edge, right? Already. What's next?
5.
5. Let's mark that edge because that's being used already. What else?
1.
1. So I'm gonna mark this edge being used. Yes, next.
And then 4.
I go to 4. Okay, so now I mark this edge from 4.
Yeah, then kind of go around the pentagon so you get that 4.
So after 4,
So go around the pentagon.
like that, 2. So now I've used this edge. 1. Use this edge. And then of course I'm going to use these edges. Sorry. No marker. So that's after 1 I get 2, 3. After 3 to 6, and then back to 4.
What about 3, 5, 5, 4?
Okay, so I missed some, right?
It doesn't matter what
So I've got to 3. Now I can go.
3, 5, 5, 4, 4, 6, 6.
I can go like this, right? So what did we say? From 3 I went to 5. From 5
Yeah.
I went to 4. From there to 6. And back to 3. Is that it?
Yeah.
That's an Euler path. It's a cycle because it ends exactly where I started. So Euler posted this question, again, long time ago. Very prolific mathematician. And he said, what's the condition in a graph for such a thing to happen? His motivation was something with geography of bridges around Paris. Paris it's a little island, was much more than now, with the river going around, a bunch of bridges in and out of the island. There was a question of defense. Back then, Napoleon was doing a lot of numbers in Europe, and they were really concerned, hey, well, we're gonna get wiped out sooner or later, right? So there was a real question of how to use those bridges and in what order to get in and out of Paris. So Euler, being a mathematician, thought, hey, how about I figured this out? That was the story anyway. And he was asking, what does it take for a graph to have an Euler cycle? What property do I need to have such a cycle? So I'm gonna state that property. So there exists an Euler cycle that implies all degrees of any vertex has to be even. Why does it have to be even? I mean, what do you think? Is that true? Is that true? That if there's such a going around in all the graph and ending up where I started, and I use all the edges once, is it guaranteed that all degrees are even? Why? I want a common sense argument. Yes.
because you have to have a way to get into and out of essentially.
For every time I'm coming into a vertex, I'm going out. And I cannot use the same edge twice. So either I use all the edges by in and out, or there is another pair of edges, I come again in and I go out, right? And if I still not use all the edges, later on I'll come again in and then I get out. Every time I get in, I also get out. So every edge in such a cycle. Let's now look at our cycle here and say, what did we do? We started at 3. From 3 we went to 2, so this edge is this way, right? From 2 we went to 5. From 5 we went to 1, right? I'm going to mark the blue. The edges are still undirected, but I'm marking in blue which way this cycle went. I went in 1, then after 1 I went to 4, right? It is. From 4 I went to 2. From 2 I went to 1. From 1 I went to 3. From 3, 5, right? From 5 to 4. From 4 to 6. And 6 back to 3. So this argument, for every edge in to a node, there is an edge out of that node, right? So how do we prove this thing? Proof. For every incoming edge, for any vertex V, incoming to V edge, there is a unique outgoing from the edge. For example, looking at what we've done here, I'm going to say for 5, say V equal 5. For the incoming, I look at my cycle here, my Eulerian cycle, and I say, what happened to 5? I use this edge to come into 5, right? So for the edge, the first time I get to 5 was 2, 5. So edge 2, 5, this is an incoming edge, 2, 5. The pair is, this paired outgoing edge is what? What is the outgoing? When I came 2, 5, what did I do from 5? In my cycle here, this is the incoming edge. The immediate pair is the edge I went out of 5. So that's the edge 5, 1. But I'm not done with 5. This was from 2 to 5, from 5 to 1. There was later on in this cycle 5 again. I came from 3 to 5 and I got out 5 to 4, right? Right here. 3 to 5 and 5 to 4. So there is another incoming edge, 3 to 5, and pair is 5 to 4. So because this has to finish where it started and uses all the edges, around every node we can pair the edges. We can say we came in this way, we get out that way, that's 2 edges. Then later on we came in this way, we come out that way, that's another pair of 2 edges, so on and so forth. So all the edges have a natural pair. It means that the degree have to be even, right? So if I have more coming into 5, I'm going to sum this up, but that means overall, so that's plus 2 to the degree, because there's a pair of edges, plus 2 to the degree of 5. So overall, the degree of 5 has to be even, because in this cycle, every time I'm coming in, I have to get out. Right? Who's with me? Good. But you know what Euler did after he figured this out? He said, what about the other way? If a graph has all these degrees even, can I find a way to go around it? So it's the opposite implication. As we know, this is not equivalent, right? The fact that every graph with the Eulerian cycle must have even degrees, all of them, It's not guaranteed logically that the opposite is true. So he was wondering, if somebody gives me a graph where all the degrees are even, can I construct a path? So he was curious about two things: whether the path exists, and if it exists, how to find it, how to actually, give somebody, there you go, like a military person, that's your path. Or a post courier message, that's how you go, depending on the application. So what happens if all those degrees are even? Let's draw a random graph with even degrees and say, I don't know, I don't have one ready. So here's one with, say, 5 degrees. If I draw it like that, everybody has degree 2, right? Is it true that in here I can trivially find Euler cycle? Of course, this is a circle, how it's called. A circle. This is called a circle graph, or some people call it a cycle, a simple cycle. So it's just one cycle, that's it. Obviously, that cycle is an Euler cycle because it uses every edge once, and it gets to, it starts from here, it gets back to here, right? What if I say, okay, that's fine, so I can easily find it in here. What if I have more edges? So I'm going to add, say, these 2 edges. Is that now what happened? I changed the degree of these 2, 4. It's still even. Are those still valid now, those 2? Why? Because they're not even. So how about I add more things? How about now? Are those everybody even now?
No.
No. How about now?
Yes. I think so.
Now everybody's even, right? Can I find a Eulerian path that does the thing? That's an exercise for you guys. To say, okay. By the way, this has another name. This is called a clique. Or this is clique of 5 because there are 5 nodes. Or it's called a complete graph. Of 5, which means all the edges. This has a name. Again, this just for reference, I'm going to draw it again. This is called C5 with the letter C from circle. This is called K5 from complete. In German, complete spells with K. So, we got a K there from complete. Germans figure out mathematics when, the other countries like, say, United States and Australia and China were fighting wars, getting on drugs, all kind of things. So Germans that was the golden era of German mathematics. Between 1700 and 1800, they were the only ones doing it, okay? So everything came from German, has a German name between 1700 and 1800s. So all the math happened in there. Germany and, at the edge of the States. Eventually they went to big wars, as you guys know, World War I, World War II, and then no math anymore. All the math after this came from other places. This is a circle or a simple cycle. This is a complete or a clique. That means I have all possible edges in there. So how about back to this statement? If I have even degree, I can construct an Eulerian path that goes through all nodes, ends up where it started, and uses all the edges. You guys are going to have to prove this at home. But the proof it's easy. I'm gonna start it now. I'm gonna say, what if I construct not an Eulerian cycle, but just some cycle? So I'm looking at this graph and say, how about I construct, here's a cycle, right? I go from here to here, from here to here, and from here back. Is that a cycle? So the cycle I draw here would be from A to B to C to D and back to A. Is that a cycle? So now that I have a cycle, how many on each vertex that's encountered in the cycle? E is not in the cycle, so I don't worry about E. But for each one of those vertices in the cycle, how much of the degree I'm using with the blue stuff? Exactly 2. If it's a simple cycle, it does not repeat the vertices. So because it only goes to C exactly once, it's incoming to C and outgoing to C. So a blue cycle, a simple cycle, is that does not repeat vertices, right? So let's write that down. Simple cycle does not repeat vertices. Like this cycle here. My cycle was A, B, C, D. Simple cycle. It means it uses degree 2 of each node vertex degree. 2 of each vertex degree. Correct? If I have a simple cycle, every vertex has an incoming edge and an outgoing edge. So out of degree of a vertex, which in this case it's 4, right, for every vertex, I've been using 2. So how much is the remaining degrees? If all of them were even, if I take 2 out of every one I'm using, what happens with the remaining degrees? So the initial degrees were 4, 4, 4, 4, 4. Now my cycle uses 2 of A, B, C, D. If I ignore the cycle, I say I've already used those degrees. So how much is the remaining degree in A? 2, 2, 2, 2. This guy still has a 4, right? Those are still even, all of them. So I keep applying this mechanism. Find another cycle, right? Can try to find another cycle in here. So I'm going to start in E and say, okay, I go from E to D, maybe, from D to B, and then I go from B back to that. I don't know if this is going to work out. Let's see. It's another cycle. This cycle is going to use, so that's the EDB cycle. How much is going to use of those each vertex visited degree? This red cycle is going to use 2 degrees of B, 2 degrees of E, and 2 degrees of D. Every simple cycle has to use for every vertex exactly degree 2 because it's an incoming, outgoing, and because it's simple, it's not going to repeat that vertex. Every vertex you see it on incoming, outgoing, that's it. So now what are my remaining degrees at this stage? How much is remaining in B? 0, because I've used all the edges in B. How about E?
2.
How about D?
2. 2.
Still even, right? Because with every cycle, I got those even 2, 2, 2, 2s out. I still have it even. So I keep repeating the same process. Okay, if I'm not done, have I used all the edges? No. So there must be another thing to do in here. Is it? Yeah, I could go from E to C, and from C to A, and this uses the 2 to 2 remaining ones, right? So the last cycle is ECA. Cycle uses remainder. This is a very constructive proof. It not just shows that this is indeed true, that if all the degrees are even, you can find such a cycle. It actually tells you how. You find a cycle, any cycle you want, remove those degrees and the edges, because you can't, in an Eulerian path, you can't use an edge more than once. So once you use an edge, you have to take it out. Then you are either done, you use all the edges, or there is more cycles to be found. You found another cycle, You add it to your path, and another cycle, and so forth. So the only thing remaining is to glue this together. If I found those cycles, can I glue 3 cycles in an Eulerian path? No, right? That's very easy to see, and you can do it as an exercise. Since I found those 3 cycles, could I have come up with a way to visit all the cycle edges here, and all the cycle edges here, and all the cycle edges here, kind of in one big round, and start from A, for example. How do I glue these two? A, B, C, D is a cycle, E, D, B is a cycle. How can I make out of these two a big cycle? What's the internal mechanism? I go from A to B to C to D and back to A. If I'm back to A, I can't continue doing this, right? So let's take that picture separate. Let's say if I have A, B, C, D, that's my cycle. A, B, C, D, right? And I have an EDB cycle in there. E is somewhere in here. It's an EBD cycle. How can I glue them into one piece?
Start at B or D.
Right. Start at, say, B or D, and then when I'm back, I can go this cycle, then follow the other cycle, right, for example. Or even if I want to start here, A, B, I have to stop in the middle, not follow that cycle. I stop at B. At B, what do? Follow the other cycle, and then continue this cycle, right? Because the other cycle is going to end up at B, right? So how do I glue cycles that have an if cycles don't have an intersection, I can't glue them. There's a circle here, nothing to do. But if they have an intersection, I go follow the first cycle up to B or D, which one is here, B, and then I don't go continuing that cycle. I do the other cycle, I'm back at D, so then I finish this cycle. So I could say, go from A to B, now I'm in B, I go from B to E, from E to D, back to B. Now I finish the second cycle, I'm back at B, so I go C, D. So cycles with an intersection can be made into a bigger cycle with repeating vertices. That's why if I found a cycle that uses all my degrees, at the end I have degree 0, I could glue those 3 cycles into an Eulerian path. This proof took another 150 years since Euler stated the problem. He did it immediately one way. The other way, a complete proof, only existed 100 years later. So since we're here, how about a different problem? Also very important, actually more important than this one in computer science, which is the Hamiltonian cycle. Use every vertex exactly once. So here's the graph. There's a big graph to this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the edges are what's called in a planar graph. In a planar graph, if a graph is planar, there is a way to draw it so that the edges don't intersect each other. Like in here, you see I have edges that if I do it in 2D, those edges will intersect in a plane. Maybe if I draw this graph in 3D, I will have a way to avoid intersections. But the graph is called planar if there is a way to draw it so that the edges don't intersect. Question?
Can all graphs be drawn in 3D so the edges don't intersect?
I think so. Because in 3D there's a lot of space. Right? But here's a planar graph, and we draw all these edges that we see next to the, actually not all of them. So there's no edge here. The graph, right? Planar because edges don't intersect. Doesn't have all the edges. See, like I could have drawn more edges in here, 6 to 7. So is there a Hamiltonian path? A path that uses not all edges like before, but all vertices exactly once. Can I draw cycle means I have to start somewhere and end up where I started. And I want to use all the vertices exactly once. Can I do that? So again, cycle means I start and I end in the same place. Hamiltonian means I have to go through every vertex exactly once. Yes?
Start at 1,
Yeah?
go to 4, and then to 7,
Where?
to 7, then to 5, up, and down to 2, then up to 3, then right to 8, then down right to 10.
Am I worried about not using an edge necessarily? No, I don't have to use all the edges here. In the Eulerian path, I have to use all the edges. What's next
Up
after
to
that?
13, down to 12, down to 9, down to 11, then up to 6, and then up to 1.
Is that doing it? Is he going through all these vertices exactly once? Very good. Huh? So, nice, right? This is an actual important problem. It has practical implication much more than the Eulerian problem. You're going to hit this problem in computer science a few more times. It's the issue of a person with a mail going around to all these houses. And you know, how do I visit all the houses? I don't want to visit the house twice, right? And there's some other constraints that could be applied to it, right? A lot of networks, whether this airline flights or mail delivery or other things, would like to visit each node once and be economical about. Economical is a notion we haven't defined yet, but there is certain constraints and costs associated with traveling in a graph. Turns out this problem, which is like before, like Euler, what does it take to exist a Hamiltonian path, right? Euler answered the other question, Eulerian path. He proved it one way and made a conjecture that that's actually if and only if, like if it's all the degrees are even, then it goes the other way. And the proof, as you can see, it's pretty simple. In here, the question is when G has a Hamiltonian path. This is a very hard problem. Perhaps some of you have heard of so-called NP problem. When you're going to study theory of computation, you're going to define a class of problem called NP or NP hard problems, for which there is no good algorithm to solve it. We can solve it by brute force. We don't have a way to solve NP hard problems efficiently with a computer. So there's an entire theory that you're going to study in theory of computation that defines this is one of the problems. There's a bunch of problems that are all NP hard, meaning there is no efficient solution algorithm to do this. You just try every possibility and see if it works out. This is one of the NP hard problems. And because it has practical aspects, people have tried with approximation and randomization to estimate whether there is a path. We know the mathematical properties necessary for having a Hamiltonian cycle, but that property doesn't necessarily help us in building an algorithm. Like you saw in the other problem, the property is to have even degrees. that actually tells us how to find an Eulerian cycle. You find a cycle, find another cycle, find another cycle, glue them together. In here, the notion that we need is something that we can discuss in this class. It's called closure, and we understand how that plays out, but having an algorithm based on closure is not easy. So you have to wait for algorithms and theory of computation to figure out why this problem is so hard. Why can't I just give me a graph? I'll tell you if there's a Hamiltonian cycle in it. Easy. Not easy. Right? So that's about this. I want to mention two more things here before I so we talked about cliques, we talked about subgraphs. Another thing that you have to know, two more things about graphs in the introduction, is the concept of bipartite. It's very easy, this one. This one said if I have this, usually that's a typical notation, V is the set of vertices, E is the set of edges, right? So this is vertices, like sometimes called V, and this is edges, as in pairs, U, V of vertices. Bipartite means V can be partitioned in two sets disjoint. So the set of vertices can be partitioned such that all edges are from A to B. So here's a bipartite graph. Vertices are partitioned into two sets. So there's either left side or right side. And every edge has to be between those two sets. Something like that. So no edges inside A, no edges inside B. Doesn't mean all the edges have to be there. I mean, I could have a point here that has no edge at all. That's okay. It only says the edges have to go between A and B. That's what bipartite means. Bipartite graphs have enormous implications in computer science. A lot of problems can be solved with bipartite graphs. All the matching problem, every time you have to do any sort of matching, it's typically a bipartite graph problem, right? So it's very simple to say what it is. There's a theorem, just like in these other cases. What does it take for a graph to be bipartite? Right? So we've seen Eulerian cycle. What does it take? Edges have to be even degree. Hamiltonian cycle, what does it take? The closure of the graph has to have some property. You'll study that in algorithm. What about here? Obviously, not all graphs are bipartite, right? There are some graphs that cannot be partitioned into left versus right. So the theorem says G is bipartite if and only if all cycles are even. Even meaning, when you go around from an edge to the vertex to itself, you have to go an even number of edges. So one way, it's extremely easy to prove this way. If it's bipartite, why is it that any cycle has to be even? For example, here's node 1, 3, 5, 7, 9, and here's 2, 4, 6, 8, 10. What's a cycle in here? Can anybody show me a cycle?
One, two, three, four, 1,
Why is it that if the graph has this structure, left versus right, and all edges are flowing from left to right, all the cycles, if there are cycles, I'm not saying they have to be, right? I could have a graph with no cycles at all. This graph has no cycles. But if there is a cycle, why is it has to be even? Guaranteed, even. If I have a cycle, it must be even. Why is that?
Because all the odd numbers pass you over to the other group, so that an even number per cycle would pass you back to the side that you started on.
So to have a cycle, I have to end back on the same side I started, right? Right? If you start from 1, a necessary condition to end back at 1 is to end back on this side. But to go back on this side will take 2 edges. Because any edge will take me from here to the other side. To go back, I need to go back to another edge. So if I'm to get back to 1, jump this way, that way, this way, that way, that way, this way, so on and so forth. If all the time I'm on this side, means I've been an even number of times. And every time I've been on this side, it's an odd number of times. Because there are no edges in here and no edges in here. So again, any cycle will be left. A cycle starting inside A will have to go A to B to A to B to A to B back to A. Right? A I mean everywhere on this side, B I mean everywhere on this side. Any cycle that starts in here will have to jump around and end back in A. That cannot be done with an odd number of steps. It's guaranteed AB and back BA, and then AB and back BA. So if I'm in A, it's gonna be an even number. Who's with me? Okay? So that is guaranteed to be an even number. Okay, that's easy. How about the other way? If all cycles are even in this graph, I'm not showing you the graph bipartite. I'm just giving you a graph and say all the cycles are even. Why is it that you can construct those two sets and say, okay, if you told me all cycles are even, there is a way to group things so that one side has no edges inside, the other side has no edges inside. All edges will flow back and forth. It takes a little bit of time to do that. So the other implication, I'm going to put it here like this, from right to left. If all cycles are even, I'm going to start this proof and you guys have to finish it. I pick a vertex V, choose V, doesn't matter what vertex, V inside big V, a vertex. And design the side A, a set that says here's all the vertices with the property that the shortest path from V to X, shortest path meaning the number of edges. Shortest path will never contain cycles because once I get to a point, I just stop. That's the shortest path. If I keep going and I go back to that point, that's not the shortest path anymore. This is even. And define the side B, which says these got to be the other vertices that the shortest path from V to those vertices, let's call them Y, by number of edges is odd. Obviously that's the V minus A, because the shortest path is either even or odd. I've grouped together all the vertices, X is in here. I say all the vertices that I can reach from X, sorry, that was V. These are the other X's. The ones that when I reach from V to them, it will take an even number of steps. Those are in the same side as V. So V will be here. Union. V is in the side that it can reach to itself or to all the vertices that will take an even number. And B is the other side. B, those are the y's. It says to reach in here, starting from V, V is a fixed node. To reach in here, it will take an odd number of steps. So I got my partition, but what you have to prove at home is that there is no edges inside A and no edges inside B. Right? I've got a partition, so I did say left versus right. Now to show that it's a valid partition to bipartite graph, it means there's no edges around here and no edges around here. So I've done the heavy lifting. I told you how to create this partition for bipartite graphs. If all cycles are even, that's a necessary condition. Now what you have to show is that inside A cannot have an edge, and inside B I cannot have an edge. If I would have an edge, there will be a contradiction. That's your exercise for Friday. You gonna come to office hours on Friday?
Yeah.
Good. All right. So that's bipartite graphs. The other thing that we really have to talk about, extremely important in computer science, as your introduction, is trees. Trees are a very particular sort of graphs. Let's talk about trees. I have a tree here. So trees, just like all the introductory concepts, so we talked about bipartite graphs, Eulerian cycles, Hamiltonian cycles. Those are all introductory concepts into graph theory. It's the first 2 pages of a graph theory textbook. They are very simple. They have to be a graph G that's connected. So no disconnected nodes. And it has no cycles. That's a tree. It's connected and no cycles. So I'm going to draw one here. Here's A. Draw it properly. A. This is E in my drawing here. E goes to B. This goes to H. I. This is F and G, and A also connects with this node here, D, which connects to M and L, and A connects to C, which also connects to K and J. Is this a tree? Is it connected? Do you see visually 2 parts or 3 parts of it? Do you see everybody connected with everybody? Nice. It has any cycles in it? No. That's a tree. Must be a tree. So because it has no cycles, as an exercise, I'm not going to answer it as an exercise. How many edges? So let's say G is B and E, like before, right? And N is the number of vertices. That is the size of V. I have N vertices. How many vertices I have here in this tree? 1, 2, 3, 4, 5, 6, 7, 10, 13, right? Which is the size of V. So what I'm asking you guys for this such a particular structure, how many edges have to be there? In a general graph, every possible edge can be or cannot be. But in a tree, it is true that I don't know which edges are in. I could delete this edge and add this edge instead, and that's still a tree, right? So there's no guarantee that a particular edge is in there. But the number of edges, you should be able to calculate because there are no cycles. So before you do the homework, by the way, you should answer this question, because if you don't answer this question, you're going to get stuck in the homework. A tree It's very easy to tell how many edges are there if you know how many nodes are there. If for 30 nodes, there gotta be a certain number of edges. And that's the question you should answer before doing the homework. Now, this is undirected. Undirected on a tree typically means no designated root. We all see trees that have a root, a starting node, right? How many people have seen trees like binary search trees or sorting trees, right? They have a root, right? Typically in computer science, we draw the root at the top, while in nature, the roots are down, right? Now, if I designate a root, I'm essentially directing edges. Because the direction is going to be from the root. I can pick anybody to be a root in a tree. If I don't have a designated root, I can pick any root I want. The moment I pick that root, I've already decided the structure of the tree flowing from the root to the leaf. So I'm going to pick the root A. What it's going to be, now that A is root, now how do I think of what's connected to A? That's the immediate neighbors. What's connected to A?
A connects to
D, C, and who else? E. Right? So I have this direction of edges implicit that says from the root down the tree, I decided what direction stuff going. So how about D? D goes to L and M. How about E? E goes to F and G and B, right? And C goes to? I'm going from the root, so C doesn't go back to A. I've already gone from A to C. Where can I go from C now? And what else? From B I can go to more places, right? H and I. So once I pick a root, I'm deciding the structure of the tree, the direction of the edges. It's implicit. I don't mean to say, if you think of a tree, again, you can pick another root and you get a different tree. In here, what's the depth of this tree? Depth is the length, number of edges, max from root to a leaf. Leaf are those guys. This is a leaf. Leaf. It's at the bottom. Only one connection. And we also have the notion of parent versus child in a tree. E is the parent of G, right? A is the parent of E. So let's write that down. E is the parent of F, G, and B. Because in a tree, everything flows. I don't have cycles, so there's only one way to go about it. What's the depth in here? Maximum number of edges from A to the leaf? Number of edges. What's the deepest? How many edges I can go deepest? This is 1, 2, 1, 2, 1, 2, 3. So depth is 3 in this tree. Right? It's the maximum number of edges I can go from root to the end, any path. Now, the same exact tree, I could have picked a different root if I wanted to. So what happens if I pick a different root? If I decide, okay, I don't like A as a root, Sometimes the root is specified by design or explicit, but sometimes it's not. Like in general, if you talk about a tree, it's just a graph connected with no cycles. So I'm going to pick another root now. I'm going to pick B. What do I get? Who's connected to B? I get H and I, and who else? E, right? Who's connected to E? F, G, and who else? A. Who's connected to A now? D and C. And I get here K, J, and I get here L and M. I've got a different rooted tree, which is the same tree with the same connections, but I pick a different root in this time, right? So now B is the root. What's the depth now? What's the maximum number of edges I can go from root down to the leaves?
4.
Okay? One thing that we have to know here is that this is a theorem, but it's obvious one, doesn't require a proof. In a tree, first of all vertices are connected. AKA reachability of UV for every vertex is true. From any vertex U, I can reach any vertex V. And the path U to V for any UV is unique. So in a tree, any way you pick two vertices, they're connected. There is a path between them. So let's pick L and C. The path is unique. There's only one way from going to L to C. Which way is that?
DAC.
Right. If I pick M to I, what's the path?
BAEBI.
Right. The path is unique. If I wouldn't have a unique path, meaning I'd have two paths, I would have what? I'd have a cycle which is not allowing trees. So visualizing this way or this way, how do I see the path in a hierarchical tree that has a root? Suppose I want to go from M to K. What do I do from M? I go up from both of them until I find a common ancestor, right? I go from M, D. Is D an ancestor of K? I want to go to K. Is D an ancestor of K?
No.
No, so I have to keep going up. I go to the root. The root is an ancestor for everybody in the tree. So then I go down to the unique path that goes to K, right? So this unique path is typically from U goes to a common ancestor for UV and then get down to V. The path has to look like this. Find the common ancestor from U there and back to V. How about, I don't always have to go to the root for the unique path. How about I want to go from F to H? What do I do? Go up to where? E. E is a common ancestor. I don't have to go to the root, right? Between F and H, I go to E. E is an ancestor of H, so there is a path going to H. The same thing could happen here. I want to go from A to H. In this case, how do I go from A to H? No, I said F to H, sorry. F to H. What would be the path in this one? I'd have to go all the way up to the root, F, E, B, and then go down to H on this side. Right? It's the same path. It's just organized differently.
This is only for undirected graphs, right?
In a tree, the concept of directed, undirected, if you draw it like this, you draw it without direction. The moment you pick a root, you effectively put a direction on edges.
Yes, but you can't go up then if you picked a root, right? So
Right.
Is it reachability?
I mean, it depends how you apply this tree to your problem. Trees are very practical structures. If you want to go up, you have a function that for every node gives you the parent. So in many computer science applications, we go up. But as far as flow goes, So in a binary search tree, there is a searching for a value that always going to go down.
Yeah.
Right? So typically in trees, when you fix a root, you imply that the edges flow one way. Or you don't pick a root and you have it in an undirected form. Okay. So that's what we have to, your problem has a lot to do with trees, your homework. The only thing that we have left is, that's the intro of graphs. In any class you take, either in math or computer science, you're going to have to do these intro concepts to go, to just be able to study anything. Now that we've done the intro, in this class the only thing left is graph traversals, which are very much a computer science thing, not a math thing. So perhaps that's easier if I show it to you on some slides. This has been a topic, I'm just warning you, this traversal thing has been a topic for final exams in every single final exam. I'm not saying that's going to happen again. Only saying, historically speaking, like, I mean, if you believe in statistics kind of thing, it always happens so far. The other instructors love this traversal stuff. So I don't like it that much because I use it in the algorithms class, but if they design the problems, if I were you, I'd make sure that, you know, I'm going to show you some slides, and you should definitely check out those slides before the final. This stuff is easy, but it's tedious. So let's see if I can find it. Okay. Do this. All right. What are we doing here? Okay, I can't see anything. The slides from the algorithms class. We're gonna go about really quick. So, an intro to graphs, why they matter. That's very easy to see. By now, most people have seen the train networks, routers, HTML pages. All those things are graph models. Graph theory is a very big subject in mathematics and computer science, and lately also in things like biology. Turns out the way nature works has a lot to do with graphs. Okay? So this is a bunch of stuff we already did. Cycles, adhesion matrices. It's everything we said. So here's a little animation of what a cycle is, right?
That's cool.
Now, this is the first traversal algorithm. What this does, it's called Bfs, Breadth-First Search. All traversal algorithms have to start somewhere. Pretty much they pick a node at random. Breadth-First Search means I visit immediately my immediate neighbors. So suppose I'm here and I want to visit all of you guys, and the adjacency is like you're next to each other. In BFS, I check my immediate neighbors first. That's the first, 6 people right here. But then I say, now that I know them, every one of them knows more people. So once I finish the first round, the immediate neighbors, I check their neighbors. So it's like waves. From Boston, where are the immediate cities I can go to? Providence and New York and Philadelphia and, Oregon or something, right? Portland, maybe. Those are the immediate neighbors. Now from those neighbors, I can go to more neighbors. And from those neighbors, I can go to more neighbors. It's like waves. So if I start in S, I start in some node there. That's my wave 0. It's only me. What's going to be in wave 1? This is a directed graph. In a directed graph, we have to follow the direction of the edges. We can't, neighbors mean you only go in the direction of the edge. If it's undirected, you can go in any direction you want. So what's going to be the wave 1? Where can I go from S immediately?
A.
That's my wave 1. Now that I've got A, B, where can I go from A and B that I've not already gone there? I won't count nodes that I've seen. A and B are in wave 1. They have the discovery time 1. So S has a discovery time of 0, because that's what I started. A and B have a discovery time of 1, or wave number 1. They're in the first wave. What's going to be in wave 2? Where can I go from A and B? I can go to D from B. I can go E. Where else? Can I go to F? No, because again, AF is is backwards edge, right? I can't follow AF. The edge is from F to A, so I can't go from A to F. It'll be against the direction of the edge. So the next round is including ED. I can reach now in wave 2 E and D. I reach D from B and E from B. When you write BFS, you have to be very explicit about these wave numbers. It's not okay. You're going to be asked, if I don't write the final exam, somebody else is going to write the BFS or BFS problem in it. I mean, it just happen every time. So they're going to ask you, what is the BFS order starting in S? And you're going to say AB is first, right? And you're going to say, then what's next? DE. Now, what can I get from DE? I can go to C. H. Can I go to G? Can I go to F? All right. So I get everywhere now. It's not okay to just say S, A, B, then what I said, DE, and da. You have to put that number there. Okay? You have to find a way to put those numbers. The right way to write BFS as drawn there is to say S is at the wave 0. Put the wave next to it. What's at wave 1? A and, what did we say? A and B? What's at wave 2? And E? Is that right? And what's at wave 3? C, H, G, F. Is the order matter inside the wave? No. The right way to put the order, though, is to say, if I have DE here, I'm going to write first the ones that are reachable from D. So who can I reach from D? Not from E, but from D. I can go to C. Where else? H and G. So those are from D, and F is from E. The right way to order, although that's not necessary, is in every wave to order the way the parents were ordered. If D comes before E, then the reachable from D will come before the reachable from E.
Does this stop?
Yes.
Does this stop you from checking something a second time? Like if E pointed back to A, would
Yeah.
you write A again and wait for
No, we don't check things again.
Okay.
There's a coloring schema in BFS. When you implement BFS, every time you reach a node, you color it in red. So then you know if it's colored in red, I'm not visiting it again. We call it like discovered already. These are the discovery times. The equivalent between D and E, they both discover in wave 2. Right? So everybody knows how to implement BFS? What kind of data structure I need? What's the obvious data structure to implement BFS? Somebody else. Yes?
Tree.
No. I could use a tree, but there's an obvious way that does exactly this. As soon as something gets in, it's ordered before other things that gets in, and then the reachable from that something gets first. What data structure facilitates that? The first in is the first that's being processed next.
Q.
Q. The right way to implement BFS is with a Q. Of course, you're going to study Qs, and you're going to study first in, first out structures and how to manipulate them and so on and so forth. That's not in this class. A Q is the right way to implement BFS.
Is that with pointers and stuff?
You can implement queues in many ways, arrays, pointers, lists, whatever it's easy. Depends a little bit on programming language. Now what's the opposite of BFS? It's not checking my first neighbors first. I check him as a neighbor, but then I don't check the other immediate neighbors. I go from him, keep going. Instead of breadth-first search, what would that be? Depth-first search. That's what you want to say? Right. So how do we do that? That's BFS implementation, pseudocode. You can take the pseudocode, running it in Python or Java, see what happens. How about DFS? Again, BFS and DFS, you gotta be fluent in those by Monday. Sorry. That's like, I mean, the good thing is about this, if you type DFS in Google, you get like 4 million results, and the first 10 of them are the best 10, and the slides, and so on and so forth. So it's plenty of stuff to do it, but don't avoid this subject because it's gonna happen. I have a different graph now, and I start here in A. I color all the edges white as in not discovered. For DFS, I have a discovery time and a finishing time. I'm gonna mark each node discovered and also finished, because in depth, once I go to him, he's discovery 1, from him I go to somebody else, but then I have to go back to him to move to another neighbor, right? Because I go depth first. So, A discover, I start from A, discovery time 1. From A, I don't move, I move to something like D, but then in BFS, what would be the next thing to do? I got D as a neighbor. Who else is an immediate neighbor of A? B and F, I'll be the BFS order. But in here it's DFS, so I keep going from D as far as I can first. So from D, I go to E, for example. E would definitely not be in the first wave of BFS, correct? For A, because it's not an immediate neighbor. That edge is not helping discovery from A. Now I finish E because I have nowhere else to go. So I mark the ending time of E as being 4. Then what happens now? I went back to D, but D is not finished. D was the parent of E. I have more places to go from D. How many people see this? Once I finished E, I went back to D. That was in my stack, let's say. And from D, I went to F. I discovered F of time 5. Gray means discovered but not finished. So A, D, and F are not finished but discovered. I finished F because I have no place to go. And I'm now back in D. Is there anywhere I can go from D? So I'm going to finish D at time 7. From D, I go back to A. Is A finished? No, because I can discover B. So in DFS, I would have spent all this time in the subtree of D, finishing everybody I can discover, while in BFS, I would have looked from A directly from D, B, and F as the first round. So DFS, depth first, as far as you can in depth. Now from B, can I go anywhere? I go to G. From G, can I go anywhere?
Yeah.
Can I go to F?
It's already discovered.
It's already black. So it's not just discovered, it's actually closed. Black means I'm done with it. So I finish G. I go back to B. Can I go anywhere else from B? No, I finish it. I go back to A. Can I go anywhere back from A? No. So that, I run everything I could from A, but I didn't finish the graph. So I start another run from C, in this case. I go to H, I finish back C. So DFS, go as aggressive as much as you can, following the subtree. BFS is the opposite. No. The immediate neighbors first. Don't advance in depth until you finish your neighbors. And then the same. Once I finish round 1 in BFS, I go to the round 2 neighbors. I don't advance in any one of those neighbors beyond until I finish the round 2. And here's the opposite. Advance as far as you can in 1 depth. And only when you finish that whole subtree, go back to your next immediate neighbor, finish the other subtree. Now both BFS and DFS creates advancing trees. The advance are the edges that allow the advance. So let's look in here. What edge did I use to advance? If I go back few of these slides. I'm moving now from D to E, right? What edge am I using? DE. That's an advanced edge for DFS. That is a part of the tree that's called the advanced tree. DFS is going to create an advanced tree. Now from E, I close it. Am I using the edge EA ever? No. That's not part of this tree because the edge EA points back to a gray node. It doesn't allow me to advance to new nodes, right? So every time I finish a DFS, I'm going to have the edges that allow me to discover new nodes. Those are the advanced edges, and they guarantee to form a tree, the DFS tree. So if I look in here now, when I go back to A, I use the edge AB or not to advance? Did I use the edge AB?
Yeah.
Edge AB is going to be part of my tree. So if I am to draw this tree that DFS creates, what is the tree? I'm only going to draw the edges that are allowing DFS to advance. From A, where did I go? D. From D, where did I go? E. And then what happened? I close this and I say, from D, can I go somewhere else? F. How about now? I go back to A, right? A to D and back to A. I go to B, right? From B, where can I go? And then from G, what happens? Stuck. I can't go anywhere. So then I start another DFS from C, and I go to H. So I have two trees in here, because I have two DFS runs. BFS would also create a tree. What's the tree here? I started in S, of course. From S, where did I go first? A and B. From A, where did I go? E. E. In E, I could have gone either from A or from B, depending how I organize my cube, right? From B, where do I go? D. And then from E, this E, I go where? F and G. And from D? Both those algorithms creates an advanced tree. And once you see the advanced tree, it will be pretty clear what happened. Now, the other edges that are not part of the tree are also important for various applications. For example, what happened in here in DFS when I saw this edge? That's not part of the tree. There was an edge FA there, right? When I see an edge from a node that I'm in to a node that it's already discovered, what is this telling me? To a node that's gray, actually. Let me show you what I mean. There was this case when I'm in F, and, I'm in E. I see this edge E going back to A. And A is not closed. A is not black. What did I just discover? A what? Cycle. Right? Whenever I see an edge that's pointing back to a gray node, means I was in this gray node, I'm still in it, and I find an edge back to it. The standard way to discover cycles is to run DFS and see if you see any edge pointing back to a gray just discovered node. And if I see no cycles, means I have a tree, right? If somebody asks you, find me a cycle, I can do it with a tree. The last thing I want to show you here, which is not part of your final exam, is this: when you study graphs next, you might put a number on each edge. Edges will have capacity and weights. So then we have a new slew of problems. Okay, well, what's the path that follows the minimum edges, or the tree that spans minimum edges? Things like that. So the graphs we've done have no edges weights on them. But there's an entire slew of problems that have edge weights on them. Oh, one more thing. In BFS, this is for the example. In BFS, what it finds is the minimum paths by the number of edges. If I start in S and I say G is in wave 3, what does it mean? Is it possible to reach G in fewer than 3 steps? No. So the shortest path by number of edges, how many edges can I go to G, is decided by BFS. I run BFS and the wave tells me the faster way to go there is the wave number. Alrighty. Done with